we have learned how to solve several types of differential equations, such as linear and separable. However, there are many more differential equations out there that do not fit into one of the types that we know how to solve. While the existence and uniqueness theorems tell us that solutions exist, how do we understand the solutions to these differential equations that we do not have techniques to solve directly? For this, there's methods to find numerical approximations of solutions to these differential equations. One such method that we'll look at now is called Eulers Method. Suppose that we want to find a numerical approximation of the solution for the differential equation given by dy dt equals f of t and y with an initial condition y of t naught equals y naught. From the differential equation, we can find the derivative dy dt at t naught y naught by evaluating our function f at t naught y naught. And recall from calculus that dy dt gives the slope of the line tangent to y of t at that point t naught y naught. In using this, we can get a linear approximation to the solution y of t near the point t naught y naught. This is given by the formula y of t is approximately y naught plus the derivative f of t naught y naught times t minus t naught. Recall that this is called a local linear approximation because it's really only useful nearby our point t naught y naught. That is, this gives us an approximation for y of t for values near t naught y naught, but is less useful away from the initial condition. So how can we get an approximation for y of t that is useful even if it's a point not near our initial condition t naught y naught? In other words, suppose that we want to find an approximation for y of b for some value t equals b, not necessarily near t equals t naught. Since linear approximations have small error locally, we can use a linear approximation near t naught to estimate y of t1 for a value of t1 near t naught. But we wanted to know y of b, not y of t naught. So how do we get y of b? The way we do this is we can incrementally get closer to t equals b by using a linear approximation of y of t at t equals t1 to find an approximation y of t2 for a value t2 near t1. And then from here, we can find a linear approximation of y of t at y of t3, which is near t2. Each time we do one of these steps, we get further away from our initial condition t naught. In incremental steps, we've moved from t naught to t1 to t2 to t3. Iteratively continuing this process, we can keep making approximations for ti plus 1 for a point near ti until we reach some nth point tn, which is equal to b. We call this change in t at each step from t naught to t1, from t1 to t2, from t2 to t3, and so on, the step size. And we can choose the step size to be h equals b over t naught divided by n to ensure that tn is equal to b. So after n small linear approximations, we move from t naught all the way to t equals b. The iterative step here is that we let t sub I plus 1 be t sub I plus h, which after I iterations is t naught plus I times h. And y sub I plus 1 is given by that local linear approximation formula, y sub I plus f of ti yi times that step size h. Graphically, what's happening is in the move from ti to ti plus 1, we're using a local linear approximation to our solution. And by making small step sizes, this local linear approximation only has a little bit of error. So at each step, there's only a little bit of error introduced, although that error does add up. So as h goes to 0, that is, as our step size gets smaller, the approximation gets better and better, but more steps are needed to find that approximation. Let's next look at an example. We'll use Euler's method with step size h equals 0.1 to find approximations for t equals 0.1, t equals 0.2, all the way up to t equals 1 of the solution of the initial value problem dy dt equals y minus 1 times y minus 3 with y of 0 equal to 2. Starting with the point 0,2, we could find an approximation for y of 0.1 using Euler's method. Y of 0.1, which is y1, is equal to y naught, which is 2, plus f evaluated at 0,2 times 0.1. Here, our function f is y minus 1 times y minus 3, so f at t equals 0 and y equals 2 is 2 minus 1 times 2 minus 3. So we have 2 plus 2 minus 1 times 2 minus 3 times 0.1, which is 2 minus 0.2, or 1.8. And now that we've found y of 0.1 to be approximately 1.8, we know that the point t equals 0.1, y equals 1.8 is nearby our solution curve. And we'll use this point, 0.1, 1.8, to find an approximation for y of 0.2. Here, y of 0.2 we'll find the same way, just with a different starting point. Y of 0.2 will be 1.8, our y value, plus f at 0.1, 1.8, times the step size 0.1. F of 0.1, 1.8, is our derivative function evaluated at t equals 0.1 and y equals 1.8, which is 1.8 minus 1 times 1.8 minus 3. So we get our approximation, y sub 2, to be 1.8 plus 1.8 minus 1 times 1.8 minus 3 times 0.1, which comes to roughly 1.704. In using this point, t equals 0.2, y equals 1.704, we can find an approximation for y of 0.3, doing out the steps here. So like we can use the point 0.2, 1.704, to find the approximation 0.3, 1.61276, we can use that point to find the next point, and to find the next point, and so on. But this process of using one point to find the next point is very tedious. So to use Euler's method effectively, we need to do many tedious calculations, where each calculation is not very difficult. This is exactly what computer programs are perfect for. These can be used to do many iterations of Euler's method very quickly.